Welcome to the second part of data handling. Today we're going to look at how we organize and put our data into a meaningful presentation so that other people can make use of the information that we have collected. The focus of our lesson will be on collecting data and then representing that data in some way. Remember from our last lesson that data was information that we collected. When we collect the information, particularly numeric information, about a topic, we say we're collecting data. Again, we had some examples last time, collecting cycle test marks in a classroom, or perhaps collecting the heights of all the people in a school. Once we have collected the data, we'll need to process that data so that we can interpret the information in a meaningful way. In our last presentation, we did that by finding some measures of central tendency or some measures of spread. Today we're going to go a little bit further and look at how we can take all the information that we do collect and put it into a pictorial or graphic representation of the data that we have collected. This will help us to make some very interesting and important deductions from our data. The process of collecting data is called primary research. It's primary because we're not finding information from books where information has been printed. We're collecting the information firsthand. There are many ways to do this. For example, I could use an interview. You've perhaps come across some of those people who sometimes sit in the mall and say, "Would you mind if I gave 5 minutes of your time?" And then they'll sit you down and ask you a variety of questions. They're doing some primary research, perhaps on a product that they're interested in seeing how well it's selling. Those questions will be the information that they use to make some important decisions with regards to what they do with that product further on. We can use a questionnaire or a survey, and we can collect the data from various sources. Designing a good interview or questionnaire or survey involves some important principles that we need to consider. Steps in collecting data. Think of a question that needs an answer. Perhaps we're interested in knowing how many people shop at Checkers. So that would be our question. Let's write it in here quickly. How many shop at Checkers? Now, answering the question is the more difficult thing. It's easy to ask the question, but how do we go about getting an answer to this question? Well, you could start in your school, and you could perhaps ask the people that walk past you in the day at school and say, "Do you shop at Checkers?" And every time you got a yes, you tick a yes and you say, "Right, we've got 1 yes, 2 yeses, 3 yeses." If you got a no, then you tick it off. And at the end of the day, you could add up all the yeses and all the no's, and if you know how many people you've asked, well, you can calculate what percentage of people do shop at Checkers in your school. But this becomes a much more difficult process when you think of asking that question to all the people in your country. We'd spend an awful amount of time collecting that kind of information. So what we need to do is design a very good way of asking as many people as possible and still getting to not spend too much time doing that. To answer our question, we need to design an instrument. An instrument is just a tool to collect the information that will help us to answer the question. That instrument could be a questionnaire, which we could hand out to many people. We could set up a table outside Checkers, for example, and interview all the people that come in and ask them if they regularly shop at the Checkers Center. We could do this for a variety of shops and collect all of that information. Collecting all the information will mean taking our telephone interviews, our sitting outside the shop interviews, and putting that all together. That will be our data for this survey. We'll also need to process that information. That means we'll have to count up how many people said they regularly shop at Checkers, how many said that they maybe only pop in once or twice a month, and how many never shop at Checkers. All of that information will be interesting to us, and especially to the owners of the Checkers corporation, because they will want to know what they can do for their shoppers. The last step in our data collection is to present an informed statement that answers our question. Perhaps we ended up interviewing 100,000 people, and from our interview we found that about 60,000 actually did shop at Checkers. That would mean that we could say something like 60% of 100,000 people that we interviewed actually shop at Checkers. Now there's more to this process of collecting data, because ensuring that the process gives us an accurate result. Remember, it's no point collecting data if we're not going to be accurate. People who have inaccurate data will not get very good results when they're actually trying to do something from the information that they've gotten. So to collect the accurate results, we need to also maintain a high integrity with regards to collecting the data. We will need to consider the sample as well as the ethics involved. And these are two things that we need to make sure are correct when we're doing some sampling: accuracy and integrity. Now, remember that a sample is a small selection of the population that we have chosen to use for the survey or interview. Even in our last example, 100,000 people is not the entire country. Do you know how many people we have in the country? There are about 50 million people in South Africa. Interviewing each one of those people would take a very long time indeed. So, what can we say about our samples? The first thing when choosing a sample of people is that the sample must be representative. Remember that we set up a table outside Checkers. If asking the question, how many people shop at Checkers, and we're sitting outside Checkers to get that answer, well, most of the people who are coming to Checkers are coming there to shop. So we would find that of all those people that we interview, probably most of them would have said yes, that's why they were there. They were coming to Checkers to go and shop. And with us sitting outside and just sampling people outside Checkers, we'd get a very high percentage of people who would answer the question with a yes. Perhaps going to sit outside Pick n Pay would mean that we'd get a very low answer, because maybe Pick n Pay shoppers don't like shopping at Checkers. Then our sample would be a large proportion of no answers compared to yes answers. It is important that we are fair to both Checkers and to Pick n Pay by making sure that we have what's known as a representative sample. That means that the people that we have asked the question, do you shop at Checkers, come from a variety of different environments. Not just those who live near a Checkers store, but also those who might not have a Checkers store nearby. Not just those who live in a city, but perhaps those who live outside of a city in a more rural setting. Ensuring that we have a good spread of people for our sample will mean that we make the sample representative. Another term that we use with regard to this is the term unbiased. It's no good trying to impress the management at Checkers by saying, yes, people are very, very fond of your store and they like shopping here. We interviewed 100,000 people and 90,000 of those said yes. But what the management of Checkers don't know is that we actually took all the people who said no and we didn't use their information. that would mean that we're making our sample biased. We're only taking the answers that we want. Now, this might sound like, why on earth would people do that? The problem is, sometimes we do this unknowingly by choosing people that actually are already biased with regards to their makeup. Let me give you an example. Say I ask the question, how many people are homeless in South Africa? And I decided to do this by actually doing a telephone survey. So I got a whole lot of numbers from the telephone directory, and I dialed them and maybe ended up dialing 50,000 people. Okay, I wouldn't do that on my own. I'd hire a whole lot of people to help me. Maybe 1,000 people could be employed, and each one of them could interview 50 people. But I collect all that data. What's the problem with this situation? Well, the thing is, I've done a telephone interview, and homeless people probably don't have a telephone. So the data that I collect, if I ask them, are you homeless? They would say, no, we have a telephone at home and you've dialed my number. I live in a home. So finding homeless people through a telephone interview is not a very good way of finding an unbiased sample. Those people that have telephones are already biased to this question, and I need to make sure that I keep my sample unbiased. What about the situation ethics? Ethics is to do with whether things are wrong or right. So respondents, firstly, have to consent to participation. Respondents are those people that we're asking the question about. If I walk up to somebody, before I even ask them the question whether they shop at Checkers or not, if I want to do a good sample, I must first say to them, are you willing to participate in our survey? I need to get their consent. Most people will not look at data if the people who have collected that data haven't got the consent of those that they've asked questions about. You might say, well, who would bother about not wanting to answer that question? Well, think about it for a moment, because we've also got to ensure that those people remain confidential. In other words, that we don't use their name. Perhaps I bump into the lady who is married to the manager of Checkers, but she's shopping at Pick n Pay. And I come and ask her a question, do you shop at Checkers? And she answers no. She might not want that information to be known by the manager who is her husband. She's maybe pretending that she does shop at Checkers, but actually she prefers shopping at Pick n Pay, even though her husband works at Checkers. She's the kind of person that we would have to ensure confidentiality for. Otherwise, that information might be what we call incriminating to her. And that, again, is something we're not allowed to do when we use samples or collect information for samples. So the two things that we must make sure of is, firstly, we are representative and that we remain ethically sound by keeping confidentiality and ensuring that people who do participate have given their consent to do so. The next step is to look at how we can represent the data. There are many ways that we can do this, and we use a set of pictures or graphs that will help us to put the data into a meaningful presentation. Now, one day you might go ahead and have a business presentation that you want to give information to the people that you're presenting to. They're not so interested in the numbers, but a diagram is often very useful for them to understand what you're trying to let them know. So we have three important ways, and these are not the only ways, but three that we're going to have a look at, different types of pictures that will help us to make sense of data. The first one is known as a histogram. A histogram is used for data that has a continuous sequential set of data. What that means is that the data is not discrete or broken up. For example, if I was measuring ages of different people, and I start and I say, this person is 5, the next one is 6, the next one is 7, and I'm counting up in years the age of the different people that I have done some sampling from. Because the ages are continuous, we don't have a break between 5 and 6. People go from 5 to 6 in one day in terms of their age, and it's continuous. This is why a histogram is very useful. So let's look at a picture of one and see how they have used the histogram to represent data. Here we have a histogram. This is a nice one from the computer because it has a 3D shape. On the left-hand side, we have the y-axis, and that's going up from 0 to 90. On the bottom, the x-axis, and this is the one that we're particularly interested in, we have the age in years. So we've gone from 6 years up to 12 years. Notice that it is continuous. There are no breaks between our blocks here because there are no breaks in age. So the heading of this histogram says the percentage of people that attend. This could have come from perhaps an attendance of a concert or a presentation and the different ages that came to that presentation. Being from ages 6 to 13, this probably took place at a primary school. So here we have a concert that was attended, and we wanted to know how many of each age attended this concert. Having a look back at our picture, we can see that when it comes to 6-year-olds, there were approximately 55. The 55 mark is over here. 55 people who were aged 6 came to this presentation. When it came to 7 years of age, there were approximately, let's say, 87. Sorry, that will be 77 because it's between 70 and 80. I'm just going to erase that for us. Let's put those two numbers again, 55 here and 77 there. The 8-year-olds were just slightly less. Let's make that 75. 9-year-olds, maybe 72. 10-year-olds, well, that was about 80. All I'm doing is I'm looking at the ages and I'm reading off the y-axis what the values are of the people that attended. Because the data is visual, we can actually see very easily some of the results from this data. For example, if I asked you the question, which age group had the highest attendance? It's very easy to go and pick that because it's the tallest column. And if I'm looking at the column, it's this one over here, the 10-year age group. They had the highest attendance. By the same token, I could also find the age group that had the lowest attendance. That's the one right here on the far right, the 18-year-olds. If I read across, I can even find that value, and that value is round about 45. Having a visual representation is far easier to work with than having just a whole set of numbers. Remember, even in our previous session, when we were organizing our numbers from highest to lowest, it was very easy to miss out one of the samples, simply because there were so many numbers on the page. The visual representation helps us to see it far easier. Also, with this set of data that we've collected here, there were many, many more samples. Adding up all those values, for example, the 55, the 77, the 75, the 72, and the 80, would give us quite a few hundred samples. And putting all of those numbers on a page wouldn't make much sense to anybody. But the visual representation makes a lot of sense, and it makes it far easier to see how the data was spread out. Bar charts are another way of representing data. They are very similar to histograms because they look almost exactly the same. Again, they are columned data that is represented in a picture form. The bar chart, however, is used for what's known as discrete data. That word simply means that one set of data does not relate to another. Remember when we were talking about ages, one age followed on from the last age. 5, then 6, then 7, then 8. But when I'm looking at discrete data, I'm looking at items in my sample that do not relate to each other, and yet things that I might be interested in. An example of this would be looking at some vehicle sales. At the bottom here, we have our list of vehicles that we are interested in. There's Audi and Mini and BMW, Polo, Jeep, a Golf, Pajero, and Ford. All of these are cars, so there the interest is the same. However, a Polo does not depend on a Jeep. They don't follow on from one another. I can't say that the next item up is the Jeep from a Polo. They're separate units. They're discrete. That's what discrete means, separate. So notice that our columns here are also separate. We haven't put them next to each other or following on from one another. It's a very small difference, but it's important. In examinations, they do not want you to draw a histogram when you should have drawn a bar chart. By the same token, you shouldn't draw a bar chart if you need a histogram. You're going to have to make the assessment of whether or not the data that you are trying to represent graphically is discrete or continuous. Looking at our chart over here on the vehicle sales, let's just move it into focus. Audi, we can say, sold 55 units during the period examined. Mini only sold about 23 units. Again, because it's a graphic representation, we can answer some very good questions. One of the questions would obviously be, which vehicle sold the best during this period? Well, that's the one with the highest column. And if we look, that's this one over here, which is the Polo. Again, we could ask, which vehicle was the least popular during this sale period? And here we would have to point to the Jeep. Now notice, we're trying to separate the types of questions that we ask. There might be some very valid reasons for why the Polo was the better sales vehicle compared to the Jeep. The reason being, perhaps the Jeep is far more expensive and only a limited number of people can afford a Jeep compared to a Polo. But that's not what we're interested in at this stage. That's why we ask simple questions from our data. Things like, which one was the best? Which one was the highest? Which one was the lowest? That keeps things a little bit more together for us. The reasons for those might come at the end of an exam question. Very often, that's what they do. They ask a question like, suggest a reason why you might have a lower sales grouping for the Jeep compared to the Polo. And then you'd have to use some initiative. You'd have to say, well, it is possible that the Jeep is far more expensive and there are fewer people that can afford one. A third way of representing data graphically is known as a pie chart. Now, pie charts are used for representing data that together forms a whole. In both the previous examples, it didn't matter if more or less people attended our presentation. If there were more, we'd simply add them in and reflect that data on the chart. In the sales of the vehicles, if we sold more or less vehicles, again, we'd simply reflect that on the chart. But when we come to data where there is a distinct whole, for example, say we were in our school, we know that there is a set number of pupils in the school. The school has perhaps 1,000 students. Now we ask the question, what percentage of those students have a motorcycle? That would divide our group into two groups. Maybe there was 100 motorcycle owners within our school. That would mean that 10% of the 1,000 people in our school have a motorcycle. We could represent this very nicely on a pie chart. Let's look at an example over here that has done that for us. I've taken all the pupils at Katlehong Secondary School. That's a whole number, a total figure. And we've divided them up into their grades. Grade 8 has got 401 students. Grade 9 has 388, 350 for grade 10, 312 for grade 11, and 245. To put that graphically, I make a circle. That's where the word pie comes from, because pies are usually baked in a round pie dish. That's why they call this the pie chart. Making a circle will be the total number of pupils in the school. So the whole circle represents the whole school. Grade 8 has got 401 students. And in relation to the whole school, they have this part of our pie. We've got nice colors here so we can see this very easily. This is the grade 9 section. This is the grade 10 section. This is the grade 11 section. And this is the grade 12 section. Now you might be asking, well, how did we draw these lines in? Is it just a random choice? The answer is no. There's a very specific mathematical method of doing this. And we're going to do this quickly now so that we can work this pie chart very well in the future. What we'll need to do is start off by getting the total number of students in our school. To get our total, we'll need to add up all the pupils. 401 plus 388 plus 350, 350 plus 312, and lastly 245. That gives us a total of 1,696 students. Let's fill that in over here. 1,696. Now, if that's the total, we need to work out the percentage of each grade. This needs us to recall the data or the work that we've done in previous sections on percentage. I'm sure you already know how to do this. Remember, to find percentage, we're going to take the value of the one that we're interested in, the grade 8s for example, and we'll divide it by the total value and then multiply it by 100 over 1. So the grade 8 percentage will be 401 divided by our total, which is 1,696. That gives us an answer of 0.23. To get the percentage, we multiply by 100. (23.6%). We can do the same for the grade 9s, and I'm going to quickly do these calculations for us. 388 students divided by 1696. That gives us 22.9%. Remember, I have to take that number and multiply by 100. 22.9. For the grade 10s, it's 350 divided by 1696, and that's 20.6%. Grade 11, 312 divided by 1696, 18.4%. And lastly, our grade 12s at 245 students is 14.4%. Now we have a percentage of the students for each grade. A way to check that you've done this all correctly is to add up those percentages and see if they come to 100%. Remember, we can't have more than 100% at the school. The school is full at 1,696 students. That is 100% of the school. That is our total. Adding those values up, let's do it quickly, just for completeness sake. 23,6 plus 22,9 plus 20.6 plus 18.4 and lastly 14.4. The answer comes out at 99.9. Well, that's close enough to the 100%. Remember, we did round off some of our answers, so that would give us a slight inaccuracy. But for the sake of our calculation, it's as close as we need to be. Now that we have the percentages, we can say that 1,696 students is the full circle. So 23.6% of the circle must be our 401 students. So this part over here is the 23.6%. This part for the grade 9s is the 22.9%. And so on around the circle, 20.6, 18.4, and lastly 14.4. Well, how do I work out a percentage of a circle? It's easy enough saying that is the percentage of the circle, but how will I have to do that when I'm drawing that circle for myself? Well, we have to start by saying there are 360 degrees in one complete circle. 360 degrees equals full circle, which equals 100% of the circle. Now, if 360 degrees equals 100%, what would 1% equal? That's right, I have to take the 360 and divide it by 100. That means that 360 divided by 100, which equals 3.6 degrees. That is the same as saying 1% of the circle. So every 1% that I have is represented by 3.6 degrees of the circle. Well, we've been given some percentages already, 23.6%. If 1% is 3.6 degrees, 23.6% will equal 3.6 degrees times the 23.6. Let's do that on the calculator. To work that out, we type 3.6, that's for 1%, and we multiply it by the percentage factor, which was 23.6. That gives us an answer of 84.96, which I'm going to round up to 85 degrees. So having a look at the circle, this 23.6% is represented by an 85-degree angle in the circle. To go and draw that, we will need the protractor again. Remember from our map work section that we always put the protractor with 0 facing to the top. We'd then measure an angle of 85 degrees and draw in the line on our pie chart. We can do this for the rest of the sample as well. The grade 9s was 22.9%. So to work out the degrees of that section of the pie, we'll take our calculator and we're going to multiply 22.9 by 3.6. That comes out at 82.44. So the grade 9 section would measure 82 degrees. Remember, the 3.6 was because 1% is represented by 3.6 degrees on the circle. We could go around the entire circle using those percentages and multiplying them by the 3.6 so that we can get the degrees for each section of our pie. And that is how our pie chart works. So, for a small recap, we've got 3 different types of charts when it comes to representing data. The first one was the histogram. That was for continuous data. The second one was the bar chart, a very similar diagram to the histogram, and that one was for discrete data. And lastly, we have the pie chart, which gives us a representation of data where there is a set whole number of units that we are going to break up into certain percentages. Let's go into the next slide and see an example. This is a typical example that you might get in an exam question. The question reads, a local car rental agency showed the following statistics for various classes of vehicle hire. In 2008, their Class 1 had 592 units hired. Class 2 had 712 units. Class 3 had 204 units. Class 4 had 156 units. In the year 2009, those statistics read as follows. Class 1 was 640, Class 2 was 750, Class 3 was 315, and Class 4, 135. Now, we want to represent this data on a table or a chart. The chart that I'm going to use is known as a bar chart. Why did I not choose the histogram? Well, again, the classes of vehicles do not follow on from each other. You might say, but surely the numbers 1, 2, 3, and 4 are sequential. That's true, but I'm not interested in the numbers here. I'm interested in the different classes. I've just given them a number form. They are not following on like age follows on 1, 2, 3, 4. So they are not sequential. They are separate or discrete units. And that's why the bar chart is the one to use here. Notice in this bar chart that we have 2 columns, a blue and a red, for each of the different classes. You can see on our little chart here that they have given us what those red and blue charts mean, or columns mean. The blue is the year 2008, and the red is the 2009. This is an example of where we have combined data into a bar chart form. We call this a composite bar chart because it involves more than one reading for the same set of data. Class 1 has got 2 readings, a 2008 and a 2009 reading. So does Class 2, Class 3, and Class 4. Grouping data together in a composite form is useful when we want to make comparisons not just across the classes, but also within the classes. In this example, it is useful for us to know which class was the best in 2008, but we could do the same for 2009. What is also interesting is how did the one class compare from one year to the next? Carrying on with this example, there are some questions which would be useful for us to answer. Question number 1. Which class of vehicle rental had the best sales over both years? Well, because we've got this very nice picture here again, we can see straight away that Class 2 outsold both or all other classes every single time in both years 2008 and 2009. They had the highest reading, above 700, both times. So the visual representation is very easy again to find the answer to the question. And we can simply say the answer to that is Class 2. Note that there is not a whole lot of calculation that has to take place once we have a visual representation. We simply have to answer the questions. And so in the exams, Don't overthink and think that you have to make a whole lot of calculations to get an answer. All you have to do is read off the picture. Question number 2 says, which class of vehicle rental was the only one to perform worse in 2009? Again, looking at the picture, every single time we see that the red is higher than the blue, except for Class 4. Class 4, the red was lower than the blue. And that means that sales in 2009 dropped for Class 4. So going to the answer, we're simply going to say Class 4. Thirdly, what was the average number of rentals for Class 3 over both years? Going back to the picture here, let's look at what Class 3 had. We're now going to have to use the table or the chart to read off the values from the y-axis for Class 3 in 2008 and 2009. Of course, we could also refer back to the original table that we were given. Remember, we would have had to come up with this chart and draw it from that table. If we look at the table in the previous slide, Class 3 sold 204 and then 315 in 2009. Going back to the chart, we can see that 204 is represented accurately in the blue column. 309 is also represented accurately on the red column. Of course, with this chart here, if we were just given the chart, we would find it more difficult to read that number accurately. I can't, for example, see that this line is meeting 309 over here. It's definitely above 300 and only just a little bit above, but it is not anywhere near the 400. If I was to do this without the information from the table, I would make an estimation, and I would have said perhaps 310 would be the answer I would get. To be within a factor of 10 for a chart like this would be quite acceptable in the exam situation. But since we do have the table and we do have those values, let's go and find the average from those table values. We said that it was 204 and 309 for the second year. Adding those two values together gives us 513. Of course, to get an average, we've got to divide by 2 because there were 2 years that we were interested in. So 513 divided by 2 gives us how much? Well, that's 266.5. Now, I'm sure nobody rented half a car. Can you imagine driving that? So we could round this off and say 267 was the average number of vehicles sold or rented out during the 2 years. Notice we have to use a little bit of common sense. We can't leave the answer at 266,5 because that's an answer that doesn't make sense. A half a car is not something that anybody wants to rent. That is why we do the rounding up. It is important that you do this in the exam situation so that the answer that you give is a sensible one. Shall we look at another example? Here is a question. What percentage of South African children do not attend school? We'll be interested in answering this question. And to do this effectively, we're going to have to come up with an instrument that will help us to do so. So the method is firstly, let's prepare a survey. That survey might be a sheet of paper that asks the question, but remember that perhaps not many of our children who do not attend school would actually be able to read. So how would we get their answers? Well, we could also set up a process where we go and actually interview and ask people directly. That would mean getting a whole lot of people to come and help us on our task. We'd have to send them all over to try and get that answer. So with our method here, preparing a survey, you might say written or interview by sending out representatives. How would we ensure confidentiality? Again, simply by including as one of the questions that we ask, do you agree to consent to actually be involved in our survey? If somebody says no, you simply leave them out and you do not take into account that you've asked that question to them because they're not going to be part of the sample or the data that we collect. Everybody who does agree, those people will then be included in the sample, and we will have to take into account the answers that they gave to the questions that we ask further. Thirdly, ensuring representation. Now remember, we've got a specific question here. So how would we ensure representation for this question that we asked? What percentage of South African children do not attend school? Now, to ensure representation, we would have to go and ask children this question. We can't ask the question of adults, because even if the adults answer on behalf of their children, what would happen is that we might go and ask children and adults, and then we ask the children the same question, and that adults have already answered on behalf of those children. That would mean that I double up on my data. And that would mean that my data becomes inaccurate. So to be really fair and to get a good representation, I would have to ask this question of the children themselves. Now, some of you are already getting clever, and you're saying to me, what if the children lie and say they do go to school when they don't? Well, that is a problem when we collect statistics. But people who do collect statistics have often taken this problem into account. And they have a sample spread that says we assume that a certain percentage will not give us the truthful answer. They've done studies on these to see what percentage of people would not be truthful. And usually these studies prove that there are maybe 1 or 2% who don't give us a truthful answer. So they allow for that in calculations at a later stage. This is not something we're going to worry about at this stage. Also, to ensure representation, we cannot move off and just take all the children from a school and ask them that question. Again, if we stand outside the school and ask how many of you go to school, we're going to get a 100% answer. We've got to go and find those children that don't go to school. So we'll have to go and send out representatives to rural areas or to the malls where kids who maybe have not attended a school are actually just hanging out for the day. We've got to try and get around to everybody that we can and ensure that we have a full representation from the total spectrum of children in our country. We'd also have to go to the various provinces to ensure representation. It's not fair just to do our survey in one part of the country. It will change when we go maybe from Gauteng to KwaZulu-Natal. KwaZulu-Natal has a different demographic for the population, and so our statistics there would be different. So we're going to have to send out a lot of people to ensure that we answer this question successfully. Once we've sent all our people out, we will call them back and say, let's see what you've collected. That's the process of collecting the data. So every person that has asked this question of the people that they met on their journey would bring their answers back to us and say, this is what we found out. We would then need to collect all of that data and put it into one format so that the people who are interested in answering this question can see what we've gained from our data collection. That's the process of organizing the data. I'm sure you can see that this process is hard work and can take a long time. Perhaps in your classroom, you can design an interview or questionnaire where you can ask a question about some of your classmates. Decide whether this process will be representative or not. ensure confidentiality when you ask the questions. Use this as an exercise for yourself to see that you can actually do this process of gaining primary research information from a selected individual or individuals. A third example will help us to use the pie chart effectively. The following information was collected at a local library: the number of children's books, teenage books, adult fiction, non-fiction, and reserve books. Now that we have the totals, it's important that we decide what kind of chart to use to represent this information. Below, I've given a bar chart. The bar chart gives us the numbers for each of the categories of books that we have used. We can see that the adult fiction category is the one with the highest number of books in this library. But what if we wanted to know the percentages of books in this library? Well, here is where the pie chart is far more useful. What we're going to need to do is find the total number of books. So let's go and add that up quickly. 3,420 plus 4,135 plus 5,612 plus 3,258 and 1,895. That's a total of 18,320 books. Let's fill that number in. 18,320. Remember, the total number of books is 100% of the pie. So the 18,320 is the 100% of our pie. Now we're going to need to find the percentage of books in each category. Again, we'll need to go back to each of the totals that we had before. 3,420 was the number of children's books. So the percentage has to be 3,420 divided by the total, which was 18,320. And then multiplied by 100. That percentage is 18.7%. For teenage fiction, 4,135 divided by 18,320, 22.6%. Adult fiction, 5,612. And again, divide by our total, 30.6% or 31% just about. And then non-fiction, 3,258. (17.8%). And the final one, 1,895. Divided by 18,320. And that's 10.3%. Now we have the total percentages for each of the books. Again, we're going to now have to calculate the degrees that each of these percentages represents. Remember, 1% was 3.6 degrees. So to do this, we have to take each percentage and multiply by 3.6. 18,7 times 3.6. So let's fill in 67%, or should I say 67 degrees, for the 18,7%. We can do the same for all the others. 22.6 and multiply by the 3.6. That gives us 81. For the 30.6 degrees, percent, 30.6% multiplied by 3.6 gives us 110 degrees. For 17.8%, multiplied by the 3.6, and that's 64 degrees. And the last one, 10.3% times 3.6 is 37 degrees. So these are the degrees we're going to need when we draw in our circle or our pie chart to make the divisions for the different categories of library books. Those values I could have filled in over here. 67, 81, 110, 64, and the last one, 37. Now we need to draw the pie chart. We're going to need those degree angles to represent the different percentages of the categories of library books that we have. The first one was 67 degrees, and that represented 18.7%. So on my pie, I'm going to draw a line starting at the top to the center, and 67 degrees would be about that distance. This then is my 18.7%. Notice, I haven't used a protractor here. I don't really need to. If you can accurately estimate where the line should go, you're going to get an accurate pie chart. Let's fill in the last couple of values. 81 degrees, that's nearly 90, is 22.6%. So another 90 degrees about there, and I've got 22.9%. 30.6%, (17.8), another 64 degrees. And my final one will be 10.31%. I've actually had one drawn out here for us so that we can see that a little more accurately. Of course, when you're drawing this for yourself, you can do the estimation, but try and be as accurate as possible. It's important that you fill in the correct values on the chart. Don't make something that should only be 10% look like it takes up 50% of the chart. That's not going to be advisable. So what have we learned today? We've discussed 3 different types of charts: the histogram, the bar chart, and the pie chart. We've seen how each one is useful for representing different types of information. You should now be able to firstly draw one of these charts if you are given information from a table. You should also be able to answer questions when given these types of charts and read off that information accurately. We will be doing further practice examples in the next session.